Bismillahirrahmanirrahim. Welcome to the second lecture about the colligative properties. And in this lecture, I will explain the first one colligative property, which is the vapor pressure lowering of solutions. And I will explain the Raoult's law, which is going to explain the lowering of the vapor pressure. So these are the different learning objectives you will learn out of this lecture. The first one is, why is vapor pressure of this solution lower than the pure solvent? And I will explain the reason with the thermodynamic parameters. And what is the benefit of the lowering of vapor pressure, and particularly in determining the molecular mass of a solute. And the third one is the derivation and the understanding of the equation used for the determination of the molecular mass of the solute. And at the end, maybe in the next lecture, I will explain further about the Raoult's law, or how can you calculate the mass or the molecular mass of the solute, and the calculation about the lowering of the vapor pressure. So what is the lowering of the vapor pressure? That means this is the non-volatile solute is dissolved in this solvent, and one of the example is the sodium chloride. It dissolves in the water. This is the non-volatile solute, sodium chloride, and the water is the solvent over here. So these pictures, two diagrams are given over here to differentiate and to affect the amount of the solute on the vapor pressure. So this is the solution, and this is the second one is the pure solvent. And you can see over here, when you prepare a solution, then this is the actually the equilibrium vapor pressure over here as compared to the pure solvent. Pure solvent, you can see this is the vapor pressure is more as compared to the solution, and the solution is less as compared to the pure solvent, and this is called the lowering in the vapor pressure. So this is the general understanding. Now coming to the reason, the first one is you can explain by using the Raoult's law. This is the formula is given over here, but later on I will derive this and explain in detail what is the effect of the amount of the solute or the mole fraction on the lowering of the vapor pressure. So simply it is given over here. This is the x is the mole fraction, and you can simply calculate the mole fraction is the moles of any of the component divided by total moles. That means total moles making up the solution. So in case of the sodium chloride in water, so you can calculate the mole fraction, the moles of the sodium chloride divided by the total moles. That means the moles of the sodium chloride plus the moles of the water, and you can calculate the mole fraction. But it is better to explain over here. That means this mole fraction is proportional to the moles of the component. So that means there will be more solute, or the sodium chloride more will be the mole fraction. So if the mole fraction is more, that means the vapor pressure of the solution is more. That means this is the mole fraction of the solvent. So if the mole fraction of the solvent is more, that means this is the how can you calculate the mole fraction of the solvent? And you put the solvent, the number of moles of the solvent divided by the total moles of the sodium chloride plus the water. So more number of moles of the water, more will be the mole fraction of the water or the solvent. So more mole fraction of the solvent, there will be more vapor pressure. And this is explained over here. Mole fraction of the solvent is proportional to the vapor pressure. And later on, I am going to give the reason why this is going to happen with the thermodynamics parameter. And this is just a graph to show the relationship between the vapor pressure of this pure solvent and the solution. And the vapor pressure of the pure solvent is more, and this is the vapor pressure of the solution is less, as explained in this diagram. So why this is happening? So I will explain with the thermodynamics parameter, which is the change in enthalpy, change in free energy, and change in entropy. So if you compare the entropy between the one, solvent, solution, and the vapor, and the entropy of the solvent is less, then the solution is more, because when you prepare a solution, solution is more having more randomness, because you dissolve the solute into the solvent, the randomness is increases. And when it evaporate, that means it is converted from the liquid to the gaseous form, then entropy of the vapor would be more. So this is the order of the entropy: solvent, then solution, and then vapor. So what is happening over here? Actually, we are going to explain the lowering of the vapor pressure of the solution. Vapor pressure of the solution means the vapor pressure of the solvent present in the solution, and as compared to the pure solvent, because always the solvent is going to evaporate, solute is not going to evaporate, because we have taken as a non-volatile solute. So what would be the difference in the free energy? And the free energy difference is, this is there are the two way: the pure solvent will evaporate or the solution will evaporate. So this is the change in entropy when the solution is evaporated. So the difference between the change in entropy of the solution or the vapor minus solution, that is called the change in entropy of the solution. And if the solvent is evaporate, then the change in entropy between the vapor and the solvent, that is called the change in entropy of the solvent, pure solvent. So you can see over here, because the solution is having more entropy, so the change would be less as compared to the pure solvent. So change in entropy of the solution is less as compared to the change in entropy of the pure solvent. So now I'm going to use the Gibbs free energy to explain the lowering of the vapor pressure. This is the change in free energy will be equal to delta H minus T delta S. And if this is similar for the solvent and the solution, because there are the similar intermolecular forces, and in case these are very similar to each other, then change in enthalpy would be 0. Then what would be the next equation? This would be 0. So delta G will be equal to minus T delta S. So as given over here, this is change in entropy of the vaporization that is smaller for the solution as compared to the pure solvent. So if the solution is having less change in entropy, that means this would be the less. So T is the constant. So delta G would have a minus T delta S, or delta G would be the less negative, because the change in entropy would be less in case of the solution. So if delta G is less or the less negative, that means vaporization of the solvent from the solution is less favored and the vapor pressure of the solution is lower. So this is the reason why the solution is having lower vapor pressure as compared to the pure solvent, because the change in entropy in case of the solution is less. So delta G would be less negative. And I have explained in the first one lecture, if delta G is having less negative, that means it is less spontaneous. So this is not going to easily evaporate. So the vapor pressure of the solution would be the less. And this is, I have just explained the previous slide. So vaporization of the liquid to a gas is disfavored by the enthalpy, because when the enthalpy is positive, energy is required to overcome the intermolecular forces or the intermolecular interaction in the liquid. So at the same time, the vaporization is favored by the entropy. That means the positive change in entropy, because molecular randomness increases when molecules go from semi-ordered liquid state to the disordered gaseous state. So more will be the positive value, more will be the vaporization. So coming to the derivation, and before the derivation, I want to explain some of the terminology which I will use during the derivation. So it would be better to understand over here. The first most important is the mole fraction. And as explained before, these are the number of moles of any of the component divided by the total moles making up the solution. And an example is given over here. If you dissolve 1 mole of the methyl alcohol in 5 mole of the water, 1 mole is 32 gram, and 5 moles of water are the 90 gram. So 1 molecule of water is having 18 multiplied by 5, that means this is the 90 gram. So of water has a methyl alcohol concentration, that means the mole fraction of the methanol would be 0.167. How? Again, you can use this formula. This is the 1 mole, because you are dissolving by taking 1 mole of the methanol divided by the total moles. Total moles are 1 mole of the methyl alcohol and 5 moles of the water. So when you solve this one, you will get the answer this. And in a similar way, you can calculate the mole fraction of the water, and by using the same formula. So moles of the water are 5, and divided by the same 1 mole of the methanol and 5 moles of the water, and the value would be 0.833. So what is interesting over here is total mole fraction. You can calculate the moles fraction of the methanol and the mole fraction of the water, 0.167 and 0.833. That means it must be equal to 1. So that means the total mole fraction will always be equal to 1. And you can use this formula to calculate the mole fraction of any one of the component if the mole fraction of the other components are known. Let's suppose I want to calculate the mole fraction of water. So what would be the mole fraction of water? So this would be 1 minus x2. So 1 minus mole fraction of the methanol. It doesn't matter, you would take mole fraction of it is x1 or the x2, but it will remain 1 minus the mole fraction of the other component. So 1 is from when you subtract the mole fraction of methanol from 1, mole fraction of methanol is 0.167, you would get the answer 0.833. So either you can use the same formula to calculate the mole fraction, or you can use this simple formula to calculate the mole fraction of the other component present in the solution. So this mole fraction is very important to understand the derivation. And now I'm going to use the whiteboard to derive the equation. about the Raoult's law and to explain how to determine its molecular mass. So let's suppose I'm starting with very simple. If this is the, I'm taking this P1 is the vapor pressure of the solution, vapor pressure of the solution, just using a abbreviation. It's better to take your own notes. So vapor pressure of solution mean vapor pressure of the solvent in the solution, and P naught is the vapor pressure of the, this is the vapor pressure and of the pure solvent. So this is the vapor pressure of the pure solvent, and I will use X1. This is the mole fraction of the solvent. And I will use X2. X2 would be the mole fraction of the solute. So this is just to differentiate. So I am using the one for the solvent, and the 2 for the solute, and 0 for the pure solvent. So this is also a solvent, but the solvent in solution. Okay, so this 0 is the pure solvent as given over here. This is the P1. P1 is the vapor pressure of the solution, or the vapor pressure of the solvent in solution, and this is the mole fraction of the solvent. This is the mole fraction of the solute. So what is happening over here, as explained before, the vapor pressure of the solution or the solvent in solution is directly proportional to the mole fraction of the solvent. So more will be the solvent, more will be the vapor pressure. So when you dissolve a solute into the solvent, that means the solvent is going to reduce, the vapor pressure is going to reduce. So if you remove this proportionality constant, you have the constant, to remove this proportionality sign, you would have a constant on the right hand side, and this constant is called the P naught, and P naught is the vapor pressure of the pure solvent, and equal to X1. So you can calculate, and this is, you remember, we previously we have explained, this is the Raoult's law, the vapor pressure of the, this is the solvent in solution. Vapor pressure of the solution is directly proportional to the mole fraction of the solvent. So this is the Raoult's law. So if you want to get the value of the X1, that means mole fraction of the solvent, and that would be equal to P1 divided by P naught. And this is another way to calculate the mole fraction by using the ratio between the vapor pressure of the solvent in solution, or the vapor pressure of the solution, divided by the vapor pressure of the pure solvent. So moving to another way, or to further explain or to further derive the equation, I'm going to subtract this one from minus from 1. So this would be 1 minus X1 and equal to 1 minus P naught P1 over P naught. So this is, I have just subtracted this by 1. So this would be 1 minus this, and this would be 1 minus x1. So as explained before, the total mole fraction, that means the total mole fraction x1, it is x1 plus x2, and this would, if there are only two components, this must always be equal to 1. So if you want to get the mole fraction of the solute x2, and this would be the 1 minus x1. Actually, why I have subtracted, because I want to replace the mole fraction of the solution with the or the mole fraction of the solvent with the mole fraction of the solute. So this would be the 1 minus x would be equal to x2 as explained above. And this I can further, you can take the LCM this one, and this would be equal to, I will explain in the next slide. So as explained, this would be the x2 and equal to, when you take the LCM of the previous equation, this would be the P naught minus P1 divided by P naught. And this is P naught minus P1. P naught is, remember, this is the vapor pressure of the pure solvent, and P1 is the vapor pressure of the solvent in solution, or simply you can call it vapor pressure of the solution. So what is the, actually, if you subtract total the vapor pressure of the pure solvent from the vapor pressure of the solution, vapor pressure of the pure solvent will always be more as compared to the vapor pressure of the solution. And this, you can simply say this is the change in the vapor pressure, but this is not only the change in vapor pressure, this is called the lowering of the vapor pressure. So this is simply the change in vapor pressure of the pure solvent and the vapor pressure of the solution. This is called the change in vapor pressure. But here, this change in vapor pressure, actually, this is called the lowering in vapor pressure, because this vapor pressure is more as compared to the this, and the change would be lower, giving the difference. That difference will give you how much the vapor pressure is lower. That's why delta P is called the lowering of the vapor pressure. So putting the value of the delta P over in the above equation, this would be x2, and this delta P divided by P naught. Okay. And now this is the equation. Now I am going to use, because our target is to calculate the mass of the molecular mass or the molar mass of the solute. So I am going to further expand this equation. So I'm again writing delta P over P naught equal to, no, I'm expanding the x2. X2 is the mole fraction of the solute. So I'm replacing over here. This is the mole fraction of the solute. It is N2 divided by the total moles. Total mole is the mole fraction of the solvent plus mole fraction of the solute. And as you remember, 1 is for the solvent, 2 is for the solute. So because the number of moles of the solute are much less as compared to the number of moles of the solvent, because this is particularly for very dilute solution. So when the solution is dilute, then the number of moles of the solute are much less as compared to the number of moles of the solvent. So in the denominator, we can uh, actually neglect this one as compared to the total value of the N1. So our next equation would be the delta P over P naught equal to N2 divided by N1. So I have neglected this one as I explained before. So these are the number of moles of the solute divided by number of moles of the solvent. So again, I am further using expanding the number of moles of the solute. That means moles are the given mass divided by molecular mass, and this is also given mass divided by molecular mass. So given mass of the solute, given mass of the solute divided by molecular mass of the solute, and this is the given mass of the solvent divided by the molecular mass of the solvent. So I'm going to further expand this equation by writing like this. So this is again delta P and P naught equal to W2 over M2 divided by, this is the given mass, weight per molecular mass, and this is called the number of moles. So number of moles are the given mass divided by the molecular mass. And the similar way for the solvent, this is W1 divided by M1. So when you rearrange this one, this would become, this is the same, equal to W2 divided by W1, and just rearranging the above equation and multiply M1 divided by M2. So this is the double fraction. So this is moving up and this is going to be down. So actually this is the final equation, and now you can calculate the molecular mass of the solute. This was our target, to calculate the molecular mass. So M2 will be equal to, and this is the, because here you want to get the value of this and then just rearrange this equation, that would become W2 divided by W1 and multiply by P naught divided by delta P and multiply by M1. So this is the final equation. By using this equation, you can calculate the molecular mass of the solute you have dissolved to prepare the solution. And this is very important, because you can calculate the molecular mass of the solute present in the solution. So this is all about the derivation, and I will explain the next, the calculation, some of the calculation in the next lecture.